Complex cognitive phenomena are often difficult to grasp and formalize in a way that encompasses its functionality compactly. Attractor Dynamics would offer here a unifying framework for understanding what is computed by cortical systems. We attempt to view the cortex as a dynamical system in which large populations of neurons form stable patterns of activity through recurrent excitation and inhibition, sustaining elevated firing, a persistent state, after an initial cue has already gone. These stable states, called attractors, function as the neural substrate for memories, decisions, and perceptual representations. Antagonists to this stability, in the form of noise and random fluctuations in neuronal firing, can likewise explain why cognition and memory sometimes fail, specifically why thoughts fragment in psychiatric disorders such as schizophrenia and OCD, and it even addresses the old-age question of free will itself. To think about the brain as a dynamical system means treating neural activity not as isolated spikes, but as trajectories evolving in a high-dimensional state space defined by the firing rates of populations of neurons. At any given moment, the network has a state, and recurrent synaptic interactions specify the rules by which that state changes over time. The metaphor of an energy landscape is useful here. Certain states are stable. If the system is pushed by a small perturbation, the activity flows back to that point. These are attractors. Others are unstable, like balancing a marble on a hilltop. Formally, in so-called auto-associative attractor networks, stability arises from Hebbian plasticity. When two neurons are co-active, the connection strengthens according to a simple associative rule, where Yi and Yj are the firing rates of postsynaptic and presynaptic neurons, and W is the synaptic strength linking them. Through this mechanism, an entire pattern of neural activity essentially sculpts its own basin in the energy landscape, making that memory or representation self-sustaining. John Hopfield in 1982 showed that in networks with symmetric strength, the dynamics can be described by an explicit energy function. Here, the system evolves by always moving downhill in this energy landscape. The spontaneous baseline firing is itself a shallow attractor, a small valley. A strong cue can push the system into a deeper, more stable valley, corresponding to a memory recall or a categorical decision. There are thus two main features that determine stability. For one, the basin depth, shaped by the synaptic weights, where deeper valleys mean more robust memories or decisions. Secondly, the noise amplitude, emerging from the probabilistic firing of neurons, where larger fluctuations can push the system over ridges into different attractors. We can say that shallow basins plus high noise yield fragility, while deep basins with low noise yield rigidity, which will be of importance when interpreted in terms of cognitive phenomena. This framework is not merely mathematical. It reflects how cortical circuits are physically built. Pyramidal neurons in the cortex sit just below firing threshold and receive thousands of excitatory and inhibitory inputs. Because these inputs arrive with inherently Poisson-like timing, each neuron's membrane potential constantly jitters. When a group of neurons is more strongly interconnected than the surrounding network, this noisy recurrent activity becomes self-reinforcing. Once a subset is activated, the feedback loops keep it active, while inhibition stabilizes the overall pattern. A minimal but biologically realistic cortical attractor circuit consisting of selective pools contains pyramidal neurons whose recurrent synapses have been strengthened through Hebbian learning. These enhanced intrapool connections, denoted W+, allow activity in a pool to sustain itself after an input disappears. The network has fallen into a deep attractor basin. The remaining excitatory neurons form a non-selective pool that provides ongoing background activity. Balanced against this excitation is a dedicated pool of inhibitory interneurons. These neurons stabilize the circuit by preventing runaway excitation and shaping the competitive interaction between S1 and S2. Biophysically, stability in these attractors relies on low NMDA receptor occurrence, which prolong synaptic integration and make the persistent state robust, while fast AMPA occurrence transmit rapid changes needed to initiate or switch states. With just these four components, the network can reproduce core cortical functions, such as holding a memory across delay, resist or succumb to distractors, and settle into one of two competing decision states. The same architecture, when pushed into different parameter regimes of excitation, inhibition, and noise, forms the basis for understanding creativity, distractibility, and pathological instability in disorders such as schizophrenia. For example, in attractor models of decision-making, the brain often operates in a multi-stable regime. When two decision cues are applied, The energy landscape shows two competing high-firing rate states corresponding to the two possible choices. In this situation, the system begins in the shallow basin of spontaneous baseline activity, and noise from stochastic spiking influences whether the trajectory escapes into the attractor representing choice A or choice B. This produces realistic variability in reaction times and decisions, and it naturally explains why choices near threshold are slow and noisy. There is an alternative regime in which the decision cues are strong enough to destabilize the spontaneous state entirely. In this case, the energy landscape no longer contains a baseline valley. Instead, the system undergoes a bifurcation, and the spontaneous state becomes an unstable hilltop. Activity is then forced to roll into one of the two decision attractors. Noise does not decide whether a transition occurs. It only biases which of the two high-firing states wins. This mechanism can explain fast and relatively deterministic decisions. These same stochastic dynamics also have implications for how we might understand free will. Because neural decisions emerge from attractor networks operating under noise, the system is inherently non-deterministic. This becomes especially relevant when two different brain systems, an implicit, fast, emotionally driven pathway, and a slower, explicit, language-based reasoning system, both provide competing inputs to the same decision network. The attractor dynamics determine which system wins on a given trial, and noise can tip the balance. Importantly, when an action is initiated by an implicit system, the explicit system may still generate a coherent verbal explanation afterwards, a confabulation, creating the subjective impression that the conscious self authored the choice. The inherently stochastic nature of cortical dynamics may thus shape the very phenomenology of free will. Sometimes the explicit system genuinely evaluates alternatives, and sometimes it merely rationalizes decisions that noise and implicit circuitry have already selected. Creative thought can be framed naturally within the same model. If neural dynamics were entirely deterministic, the trajectory through an associative landscape representing memories or concepts would follow the same path every time. The system would reliably settle into the same neighboring attractor whenever a particular concept was activated. Thoughts would become rigid, stereotyped, and repetitive. Because the recall of one memory from another is influenced by random fluctuations in the firing of neurons, the system does not always follow the exact same trajectory, but rather transitions into a nearby attractor that is semantically related but not identical to the usual one. This produces structured deviations, leaps that are shaped by learned associations, which form the basis of creative insight. This allows creativity to be both novel and grounded. A new combination of ideas or a fresh interpretation appears, but it remains anchored in meaningful relational structure rather than degenerating into disconnected noise. Empirical evidence supports this attractor-based view. fMRI work shows that individuals with high verbal creativity exhibit greater temporal variability in functional connectivity, especially in regions such as the lateral PFC and the parahippocampal gyrus, which anchor cognitive control, internal mentation, and memory. Creativity also correlates with increased variability within the default mode network and between the default mode, attention sensory motor, and control networks. What this temporal variability reflects is not an instability in the pathological sense, but flexible reconfiguration, which suggests frequent shifts between cognitive modes, consistent with the idea that creative thought reflects stochastic but structured transitions between nearby attractor states. Schizophrenia can be interpreted as a disorder of unstable attractor dynamics in cortical networks. The central idea is simple. We know that cortical circuits normally form stable energy basins, persistent states that support working memory, coherent thought, emotional value representations, and accurate perception. Here, however, the instability can be traced to two core biological factors. For one, reduced NMDA-mediated excitation due to decreased receptor function and lower dendritic spine density, and impaired GABAergic inhibition, reducing the network's ability to regulate activity itself. Such dynamical changes map directly onto the three classical profiles of the mental illness: the cognitive, negative, and the positive symptoms. The cognitive symptoms characteristically include distractibility, weak working memory, and reduced executive control, all of which arise when persistent attractor states in prefrontal cortex lose stability. The NMDA conductance is hereby reduced. The firing rates drop, persistent states weaken, and shallow basins collapse under noise. In this condition, even small random fluctuations or irrelevant stimuli can push the system out of a working memory state, resulting in the above symptoms. The negative symptoms are behaviorally linked to emotional flattening, reduced motivation, social withdrawal, all of which are a product of reduced firing in the orbitofrontal and anterior cingulate networks. These regions encode reward value and motivational significance, using attractor states whose firing rates track hedonic and motivational variables. When these networks operate with reduced excitatory drive, their attractor basins again become shallow and cannot sustain strong reward-related states, aligning with imaging findings showing prefrontal hypometabolism. Lastly, the positive symptoms manifest in the form of hallucinations, delusions, and disorganized thought. Here, both spontaneous and persistent attractor states become excessively shallow and noise-sensitive, which is reflected in neuroimaging showing abnormally elevated activation in temporal lobe regions supporting semantic memory. Now, both NMDA and GABA function is starkly reduced, leading to statistical fluctuations that are sufficient to push the system into high activity states without external input, as well as thoughts drifting rapidly from one weakly related attractor to another, generating loose associations and bizarre conceptual linkages. The hallmark of the symptom can thus be summarized as internally generated activity being mistaken for externally driven perception. But what exactly does that mean beyond unstable attractors? It brings us to a key insight that not only connectivity is reduced, it is reduced in a specific direction. In the healthy cortical hierarchy, forward connections running from early sensory cortices up towards higher areas are strong. They carry sensory evidence, information from the outside world that continually anchors internal processing. Backward connections are weaker. They carry predictions, memories, and top-down attentional signals, so-called internal models that help interpret ambiguous sensory inputs. However, when researchers measured effective connectivity, the causal influence one area exerts on another, they found a striking pattern in schizophrenia specifically. Forward, bottom-up connectivity was significantly reduced, while backward, top-down connectivity was preserved or even increased. This directional imbalance has a straightforward dynamical interpretation. If forward drive weakens, sensory evidence loses its stabilizing influence in cortical attractor states. At the same time, stronger backward signals give excessive weight to internally generated priors, predictions, and memories. In other words, the hierarchy becomes top-down dominated. If schizophrenia can be understood as a disorder of reduced stability, the striking computational feature underlying the symptoms of the obsessive-compulsive disorder is an overstability in cortical and related attractor networks. In OCD, certain attractor basins are pathologically deep, making the network resist transitions to alternative states. This is often due to increased glutaminergic transmission, which raises firing rates and strengthens recurrent synapses. As a result, once the brain falls into a particular representational, emotional, or motor state, the system struggles to transition out, even when the incoming sensory evidence or task demands change. This single mechanism expresses itself differently depending on where in the cortex the overstability occurs. In lateral prefrontal networks, it impairs cognitive flexibility, struggling with attentional set shifting and rule adapting, coupled with persistent thoughts as well as problems to shift the mental context, which is the core of obsessions. In motor and action selection circuits, overstability traps the brain in repetitive action patterns, generating compulsions such as repeated checking, counting, or cleaning that are difficult to terminate. And in orbitofrontal and anterior cingulate regions, which, as we know, encode the emotional significance of events, excessive stability leads to prolonged negative affective states, such as anxiety or a persistent sense of incompleteness. Lastly, with regards to mania and the bipolar disorder, we can envision a computational imbalance of reward and non-reward systems. Whereas depression is reflecting overstable non-reward attractors in the lateral OFC, leading to persistent negative mood and rumination, mania arises when this balance tilts in the opposite direction. Here, the brain exhibits hypersensitive reward circuits in the medial, orbitofrontal, and pregenual cingulate cortex, combined with reduced sensitivity in the non-reward system of the lateral OFC. These two systems normally counterbalance each other, but in mania, their calibration diverges. Reward expectancy attractors become excessively excitable, whereas non-reward attractors become too weak to provide the normal braking signal. The result is a dynamical regime where small cues for success or goal attainment can escalate into runaway activation, producing elevated mood, impulsive pursuits of rewards, reduced need for sleep, and an inflated sense of self. At the computational level, both short-term reward expectancy attractors and longer timescale mood state attractors may be overly excitable in mania. Incoming reward cues drive the medial OFC into steep, self-reinforcing basins. Meanwhile, weak lateral OFC responses fail to counteract or terminate this activity. The long cortical loop through language and planning systems may then sustain these positive states through repeated top-down reactivation, essentially a manic analog of depressive rumination, but biased towards reward possibility and drive. In this framework, bipolar disorder does not reflect two unrelated conditions, but rather an imbalance between independently modulated reward and non-reward attractor systems, with mania and depression representing opposite dynamical extremes of the same underlying circuitry. We saw how the dynamical system's view can unite perception, thought, emotion, and psychiatry within one computational architecture. It shows how the same circuits that give rise to memory and imagination can, under different parameters, produce distractibility, rigidity, or episodes of extreme mood. And it suggests something deeper as well, that our mental life, its stability, flexibility, and creativity, is not the product of separate modules, but of a single set of principles operating everywhere in the cortex.